Well, welcome to a second video on Bernoulli equation. We derive the Bernoulli equation that in a fluid which is flowing steadily, okay, and it does not have viscous flow. We will talk about what happens when there's a viscous flow in a future lecture, but if there's no viscosity, or we can ignore the viscosity, the effects are negligible, all right, then we can apply work energy theorem. We can apply the energy conservation ideas, and those ideas result into this combination of things at any point is same as at any other point. Very important, right? This combination is at one point is same as at another point. So there are 2 points are compared to get an equation. All right. This by itself is not equation. This just this is same, and it's easy way to remember Bernoulli. So let's look at an example. Long ago, in a static fluid, you had this. Here's a tank. So this is a simple example. Here's a tank of water, say. So the density is rho, and this is open to atmosphere. Okay, so I want to compare this point and this point. We can I want to know what's the pressure over here. What's the pressure over here? So that's my question. If the over here is P0, P atmosphere, you probably right away know the answer. You say, I don't need Bernoulli. I'm just going to be able to tell you the answer right away. So answer is, without thinking, just from the static fluid case, you say P, let's call it 0.2. I'm going to call it 0.1. And so P at 0.2 is equal to atmospheric pressure plus rho density times G times H, right? And that is correct. All right. I didn't use any Bernoulli here. I just had this, some other time we had definition of pressure, and we applied that and we got this. All right. Now I'm going to do the Bernoulli for this. All right. And we'll see that really it is automatic in Bernoulli. So it says this is something I already know, that atmospheric pressure, right? So if I take this as property, place 1, and I write this combination at that, and I write the same combination at that place. All right. So if I take the height as 0 here, so this is P1, V1, and H1. I need to know those things, and I need to know P2, V2, and H2 to apply Bernoulli, right? So P1, we know that that's equal to atmospheric pressure, because that's the one it's pressing on. So at this point, I'm looking at this fluid system, and it's being pressed by atmospheric pressure there. V1 is 0, it's not flowing. H1 is, if this is the 0 height, then H1 is equal to H. P2, well, what's the pressure from outside the system, right? So this is the system. We're thinking this is the system. So one pressure will be that way, another pressure will be that way. That's the pressure I want. So that's the pressure I want. V2 is 0, H2 is 0. So this combination at that is P atmosphere plus 0 plus rho GH H1. So P1, so this is P1 plus half rho V1 square plus rho G H1, this side. That's equal to P2 plus half rho V2 square plus rho G H2. So P2 is the P I want. That's the P2. And this is 0. And this is also 0. So P2 is P atmosphere plus rho GH. That's using Bernoulli. So exactly the same as what we had last time we studied.